Time to start Chapter 3, Section 5. And this section deals with rational functions and their graphs. The objectives here at the bullet points. One, find the domains of rational functions. Use this new arrow notation. Identify vertical asymptotes of the function. I think that's what we'll get through today in this video. And then we'll talk horizontal asymptotes later. Move our function graphs around a little bit, shift them left, right, or up and down. Graph rational functions, find these slant asymptotes. We've found horizontal asymptotes, vertical asymptotes. There are slanted ones also. And we'll solve some applied problems with rational functions. Okay, let's get started. Rational functions are quotients of polynomial functions. Remember, a quotient's just a fraction. So we're going to put polynomial functions in the form of a fraction. This means that rational functions can be expressed as some function p of x is the numerator, some function q of x is the denominator. That's our rational function that we'll just call f of x. Where p and q are polynomial functions, q, of course, the denominator cannot equal 0. The domain of a rational function is the set of all real numbers except the x values that make the denominator 0. For example, the domain of this rational function here is f of x. Our numerator is p of x, denominator is q of x, and notice here the denominator is in factored form. Well, if we were to take each of these factors and set them separately equal to 0, we would find the x's that zero out the whole denominator. If we set that factor to 0, we get 0. X minus 2 equal to 0, we get 2. X plus 5 equal to 0, we get negative 5. So those are the three x values that would zero out our denominator, and therefore they are not part of our domain. So here in example 1, find the domain of each rational function. They all look pretty similar, slight differences between them. And let's see what's happening here in part A. Numerator x squared minus 9, denominator x minus 3, and the denominator is where most of the action is happening here. Remember, we cannot divide by 0, so I'm going to take this denominator and set it not equal to 0. And if I add 3 to both sides, I know that x cannot equal positive 3. And we have our choice of notation. That's an I. Domain. First, I'll do a set builder, the set of all x such that x cannot equal 3. Or you could do interval notation, going all the way left from negative infinity till you hit 3. And then you would union that with the set from 3 to positive infinity. So either of those are completely acceptable. Letter B. Denominator is x squared minus 9. We want to set that not equal to 0. And there's two ways we could do this. We could add 9 to both sides, so x squared equals 9. And then square root of 9 plus or minus 3. Or if you see x squared minus 9 and you see a sum and a difference, you could factor it further into x minus 3 times x plus 3 and set that equal to 0. And then when you set each factor to 0, you get the same plus and minus 3 that we found by extracting the roots. So, domain again, we'll write it in both possible ways, I guess. Set builder notation, the set of all x such that x does not equal positive or negative 3. Or the interval notation takes a little more this time, because we go from negative infinity to the lower number, negative 3. And we would union that with the set from negative 3 to 3. And then one more union from 3 to positive infinity. So we've covered all the numbers from negative to positive infinity except right here. Remember, we use parenthesis when this is not part of the set. Here at negative 3 and also here at positive 3. Last one. Letter C. We have a denominator x squared plus 9. Remember, we do not want that to equal 0. If I subtract a 9 from each side, now it's negative 9, and when I try to square root, I need to square root a negative number. which remember will result in non-real answers. We get plus or minus 3i. So here, the denominator will never equal 0. And you can just think about it logically. Here's some number and we're going to square it. If it's positive and you square it, it's positive. If it's negative and you square it, it's positive. And no matter what that result is, it's always positive, and we're going to add 9 more. So that denominator is always positive. It's never going to equal 0, and it can never be a negative number. So for letter C, the domain, we could write the set of all x such that x is an element of the real numbers, or you could do interval notation from negative infinity to positive infinity. That would also work. The most basic of all the rational functions is the reciprocal function, defined by f of x equals 1 divided by x. The denominator of the reciprocal function is 0 when x equals 0. So the domain of f is the set of all real numbers except 0. We would take that denominator x and set it not equal to 0, so x cannot equal 0. Let's look at the behavior of the function near the excluded value of 0. We start by evaluating f of x to numbers to the left of 0, like negative 1. If I plug negative 1 in for x, I get 1 over negative 1 or negative 1. Or if I plug in a number a little closer to 0, negative a half. 1 divided by negative a half, negative 2. Let's get closer to 0, negative 0.1. 1 divided by negative 0.1 is negative 10. Even closer to 0, negative 0.001, and negative 0.001 takes us to negative 100 and negative 1,000. As x is approaching 0 from the left-hand side, these numbers are getting bigger and bigger toward negative infinity. Mathematically, we say that, quote, x approaches 0 from the left. From the table and the accompanying graph, it appears that as x approaches 0 from the left, the function values f of x decrease without bound. We say that, quote, f of x approaches negative infinity. We use a special arrow notation to describe this situation symbolically. So as x approaches 0 from the left, we have x, a little arrow, to the 0, and the little negative up here almost looks like an exponent, but that's just telling us what direction we're coming from. We're approaching this number from numbers to the left-hand side, or on the number line from the negative side. So as x approaches 0 from the left, f of x, the function, approaches negative infinity. Observe the minus superscript on that is read from the left. Next, let's see what happens when we approach from the other side, from the right of 0. So now x is approaching 0 from the right. So here was 0 would be right here. And we can find some numbers away from 0, like positive 1, and then get closer. Positive a half, and then 1/10, 1/100th, 1/1000th. And as we plug those numbers into the function 1 over x, we get the output values of 1, 2, 10, 100, 1,000. We could plug in 0.0001 and get an output of 10,000. And then add another 0 in there, put 4 zeros and a 1, and then that would be 100,000. Mathematically, we say that, quote, x approaches 0 from the right. From the table in the accompanying graph, it appears that x approaches 0 from the right. The function values, or f of x, increase without bound. We say that, quote, f of x approaches infinity. We again use special arrow notation to describe the situation in symbols. As x approaches 0 from the right-hand side, the function goes toward positive infinity. Observe that little plus sign, the superscript on that 0 is read from the right. Because if you think on the number line, negative numbers are to the left, positive numbers are to the right. So if we have that little positive superscript as x approaches 0 and we got that little plus sign, that just means we're approaching from the right-hand side. Let's see what happens to the function values of f of x equals 1 over x as x gets farther away from the origin. The following table suggests that what happens to the function as x increases or decreases without bound. So now here we're at positive 1, and then we'll move very far away from the origin. 10, 100, 1,000. And when we make those x values the denominator of the reciprocal function 1 over x, we get shrinking values. 1, 1/10th, 1 100th, 1 1,000th. And something similar happens to the negative side as we head to the left away from the origin. We're plugging in these more and more negative numbers. We're getting smaller negative outputs, smaller fractions. -1, -1/10th, -100, -1,000th. It appears that as x increases or decreases without bounds, the function values, f of x, are getting progressively closer to 0. They're shrinking and shrinking. Figure 329, and do I have 329 up here somewhere, illustrates the end behavior as the function increases or decreases without bound. Oh yeah, that's just up here. The graph shows that the function values, f of x, are approaching 0. This means that as x increases or decreases without bound, the graph of f is approaching the horizontal line y equals 0. That is the x-axis. We use arrow notation to describe this situation. So as x heads for infinity, f of x heads for 0. And as x approaches negative infinity, our function values, the function f of x, approaches 0. Thus, as x approaches infinity, or as it approaches negative infinity, the function values are getting closer and closer to 0. The graph of the reciprocal function 1 over x is shown right here in figure 3.30. Unlike the graph of the polynomial function, the graph of the reciprocal function has a break and is composed of 2 branches. So we have this one piece up here in quadrant 1. It's stuck in quadrant 1. It has x-axis and y-axis asymptotes. And over here we have a completely disconnected piece in quadrant 3, which also has the x and y-axis as asymptotes. Looks like we got a question. And I do believe I like this one so much I do believe I put this right in your notes. What's the relationship between x and 1 over x when x is far from 0? And what happens when we are close to 0? Well, if x is far from 0, then the function is close to 0. By contrast, if x is close to 0, then the function is far away from 0. And I did like this. I had to throw that in there. Neat little tattoo there on his knuckles, the reciprocal function. So arrow notation is used throughout our discussion of the reciprocal function. It's summarized in the following box. Copy this down into your notes. So here we have x and an arrow and an a, and then our superscript is a little plus symbol. Well, that just says x is approaching a from the right-hand side. And a is just a number. So we're approaching from numbers bigger than a. Like if this was x approaches 10, we would be approaching by numbers bigger than 10, like 11 or 10.1 or 10.01. X, arrow, a, and then we have our little superscript negative sign. That just means x is approaching the number a from the left-hand side, or from numbers less than a. X, arrow, infinity means x approaches infinity. That is, x is getting bigger without bounds. And if we have x approaches negative infinity, that means x is decreasing without bounds. Another basic rational function is f of x equals 1 over x squared. Now the denominator isn't just x, it's x squared. The graph of this even function with y-axis symmetry and positive function value is shown in the figure below. Like the reciprocal function, the graph has a break and is composed of 2 distinct branches. If we set the denominator here equal to 0, we have an asymptote of 0 on the x-axis, or the y-axis is our vertical asymptote. And as we head to the left or the right, positive or negative infinity, we are heading toward the x-axis, or 0. But notice we are always heading up here. If I plug in positive values of x, positive 1, 2, 3, or 4, I get out positive outputs. Same thing happens when I plug in negative x values. I'm going to square them in the denominator and I will get positive outputs. So here I guess this kind of looks like a volcano. If I drew a little rim up there and we could draw some lava coming out. So this in my opinion is sort of like a volcano shaped graph. In addition to vertical asymptotes here. So let's look again at the graph of 1 over x squared in figure 3.31. The curve approaches but does not touch the y-axis. The y-axis, or x equals 0, is said to be a vertical asymptote of the graph. A rational function may have no vertical asymptotes, one vertical asymptote, or several vertical asymptotes. The graph of a rational function never intersects a vertical asymptote. We will use dashed lines to show these vertical asymptotes. So here you can see these little dashed lines. Those will be our lines that we approach but never touch and definitely never cross. So the line x equals a is a vertical asymptote of the graph of the function f if f of x increases or decreases without bounds as we approach that asymptote. So here the function is approaching it from the right-hand side and we're going up, up, up. There's our vertical asymptote. We're headed for infinity. Here we're approaching from the left-hand side and we're going up, up, up toward positive infinity. So as x approaches a from the left, the function approaches infinity. Here again, x is a as our asymptote. As we approach from the right-hand side, we are heading down toward negative infinity. So as x approaches a from the right, the function heads for negative infinity or decreases without bound. And our last one here, of course, again, our asymptote x equals a. As we approach from the left-hand side, we are heading down toward negative infinity. We are again decreasing without bound. So if a graph of a rational function has vertical asymptotes, they can be located using the following theorem. So if function f of x is equal to p of x over q of x, a rational function in which p of x and q of x have no common factors. That's a big one. No common factors where they've been reduced down as far as you can. And a is a 0 of q of x, then the denominator, or of the q of x, the denominator. If that happens, then x equals a is a vertical asymptote of the graph. Oops. That's the solution. Here we go. So in example 2, find the vertical asymptotes of this rational function. When I look at letter A, I see it's x squared minus 9. You know, I can factor that. It's a sum and a difference, x plus 3 and x minus 3. My numerator is just a plain old x. Can I cancel anything? Are there common factors? No. So my vertical asymptotes are where these factors are equal to 0. If I said x plus 3 equal to 0, I get x is negative 3. If I set x minus 3 equal to 0, I'll get x is positive 3. Those are my vertical asymptotes, positive and negative 3. Remember when we were talking domain, we would set these not equal to. Now we're talking about asymptotes. We want to find where they are, so this is where they are located. At x equals 3 and x equals negative 3. All right, letter B looks a lot like letter A. For letter B, denominator is the same. So when I look at that, I immediately want to start factoring. That breaks down into a sum and a difference. But now look at our numerator. X plus 3 is our numerator. So the x plus 3 we can cancel out. Now what we're left with is 1 over x plus 3. We can't factor and cancel anymore, so here's where we find another asymptote. At x plus 3 equal to 0, or at x value negative 3, we have a vertical asymptote. This one isn't because we factored it away. The last one, letter C. See, my numerator is x plus 3, just like letter B. Denominator is a little different now. Now it's x squared plus 9, not x squared minus 9. Well, let's see, to locate asymptotes, we'd set that equal to 0, and I would subtract 9, and then square root. The square root of negative 9, we know that's positive and negative 3i, but we're looking for asymptotes, real solutions, and there are no real solutions here. Or think about it this way, the denominator, we were trying to figure out where it would equal 0. Well, think about it. We are squaring whatever x is, and we're adding 9 more to it. If x is positive and we square it, it's still positive, and we're adding more. If x is a negative number, we'll square it, and then it becomes positive, and we're adding more. So this denominator, it's never going to be negative, and it's never going to equal 0. So there are no vertical asymptotes. There are no places where that denominator would equal 0, so there's no chance of a vertical asymptote. Let me pull down these. These are the graphs that went with the solutions. So the first one, we found two asymptotes at positive and negative 3. And then our function is going to be doing some stuff in between those asymptotes. For the second one, remember we factored it and we canceled out the factor of x plus 3. The x minus 3 factor that remained, we set equal to 0, and we found an asymptote at positive 3. At the other value, there's a hole in the graph. So when we factored and canceled, that exposed a pothole in the road or a hole in the graph. The one that we could not factor away turned into our vertical asymptote. And the last one, there are no asymptotes, vertical asymptotes at all. All real numbers can go into that function. So a value where the denominator of a rational function is 0 does not necessarily result in a vertical asymptote. There's a hole corresponding to the x value of a, and not a vertical asymptote in the graph of a rational function under the following conditions. The value of a causes the denominator to be a 0, but there is a reduced form of the function equation in which that value of a does not cause the denominator to be 0. Consider, for example, this function, x squared minus 4 over x minus 2. Because the denominator is 0 when x equals 2, the function's domain is all real numbers except that value 2. However, there is a reduced form of the equation in which 2 does not cause that denominator to be a 0. So if we factor the numerator into a sum and a difference, we can cancel the x minus 2 factors. Now we're left with x plus 2 over 1, or just x plus 2. In this reduced form, 2 does not result in a 0 denominator. It's still an exclusion from our domain because in the original function it does cause a division by 0. But that just tells us we do not have an asymptote, we have a hole at that value of x. So here's our great question. Do I have to factor to identify a rational function's possible vertical asymptotes or holes? Yes, it's essential to factor the numerator and denominator of the rational function. So here's our original function, and we know at the x value of 2, something's going on with the graph. Well, in this case, it's just a hole in the graph. It's not an asymptote because we could factor and cancel that x value away. All right, checkpoint 1 and 2. Just pause the video, solve those, and see if you got the answers right. Okay, checkpoint 1, find the domain of each rational function. Well, in the first one here, x cannot equal 5. If I set the denominator not equal to 0, add 5 to each side. That's my value that is excluded, or the set of all x such that x does not equal 5. In this one, I can just set x squared minus 25 not equal to 0, or factor it into x plus 5, x minus 5. And I will get x cannot equal positive or negative 5. Those are the two values that would 0 my denominator. In the last one, it is a squared quantity plus some more. That will never equal 0, so I have no vertical asymptotes. So the domain is all real numbers. Okay. Number 2 here, find the vertical asymptotes, if any. The first one, I can factor my denominator into an x plus 1 and an x minus 1. Those do not cancel with my lonely x in the numerator, so I have two locations of asymptotes, positive and negative 1. For the next one, my numerator is x minus 1. My denominator will factor, just like in the first one. So when I cancel this one, I know that's where I used to have a hole. X minus 1 equal to 0 is a hole, or x equals 1. There's a hole in the graph above or below x equals 1. When we canceled, what we were left with is 1 over x plus 1. Well, if I set that factor equal to 0, I get x plus 1 equals 0. Or at x equals negative 1 is a vertical asymptote. The last one is x squared plus 1. It's never going to be negative. It's never going to equal 0, so there are no vertical asymptotes for part C. For homework, page 406 and 7, 1 to 4, all of them, 9 to 14, all of them, same for 23 to 26, and 29 to 32. Have fun.